Now, estimating a population standard deviation or variance, use sample standard deviation or sample variance to estimate the value of the corresponding population standard deviation, sigma, or population variance sigma squared. Remember, p hat for p, x bar for mu, s for sigma, s squared for sigma squared. The sample variance S squared is the point estimate of the population variance sigma squared. To construct a confidence interval estimate of the population standard deviation, we use chi-squared distribution. This is a Greek letter, chi, it's not x, chi-squared distribution.
When products that fit together, such as pipes, are manufactured, it is important to keep the variations of the diameters of the products as small as possible. Otherwise, they will not fit together properly and will have to be scrapped. In the manufacture of medicines, the variance and standard deviation of the medication in the pills play an important role in making sure patients receive the proper dosage. For these reasons, confidence intervals for variances and standard deviations are necessary.
Let's go to the next page. Now, key points about the chi-square or chi-squared distribution. The chi-square distribution must be used to calculate confidence interval for variances and standard deviations. The chi-square variable is similar to the t variable in that its distribution is a family of curves based on the number of degrees of freedom. df equals n minus. The symbol for chi-square is this Greek letter chi, pronounced chi. So those are the chi-square shapes. Notice as the degrees of freedom gets larger, it gets a curve that gets closer and closer and similar to the bell shape of normal distribution we've seen, but it is not normal.
In a normally distributed population with variance O2, assume that we randomly select independent samples of size n, and for each sample, compute the sample variance S2, which is the square of the sample standard deviation S. The sample statistic chi-squared is equal to n over 1 times S squared over O squared, has a sampling distribution called the chi-square distribution.
A chi-square variable cannot be negative, and the distributions are skewed to the right. At about 100 degrees of freedom, the chi-square distribution becomes somewhat symmetric. The area under each chi-square distribution is equal to 1 or 100%.
When we look at the chi-square distribution, it is not symmetric. The total area under the curve equals 1. As the degrees of freedom get larger and larger, it becomes more symmetric. It doesn't go to negative infinity and positive infinity. It goes to 0 and then positive infinity. In other words, on the left side is not like the t distribution or z distribution. And this thing has a sampling distribution, which is a chi-square. And by the way, chi-squared in essence is really the same as getting to the z squared. If you square the z value, you get to chi-squared. And we can show that mathematically. So critical values of chi-squared, we denote the right tail critical value by chi-squared of the right, and the left tail by chi-squared of the left. And we get it from the table. Or, this is something that they do have some calculators that you can use. As you can see, when the degrees of freedom get larger, it gets a little bit more symmetric. And of course, don't forget the total area under the curve is always 1 because it represents the probability.
As the number of degrees of freedom increases, the chi-square distribution approaches a normal distribution, not symmetric. Confidence interval estimates of sigma squared does not fit a format of s minus e less than sigma squared less than s squared plus e. So we must do separate calculations for the upper and lower confidence interval limits. Critical value of chi-squared in the body of the table corresponds to an area given in the top row of the table, and each area in the top row is a cumulative area to the right of the critical value.
We will look at how we table. If you look at this first one, confidence interval for sigma squared or variance, n minus 1 s squared over chi-squared of the right, and then n minus 1 squared over chi-squared of the left. It's not symmetric. That's why we're not adding and subtracting e. And for sigma, we don't have to worry about that. All we have to do is take the root, we come up with the answer. So that's the idea. Let's look at a few examples. We want to find the values for chi-squared of the right and left when we are dealing with a 90% confidence interval. We want to see what we come up with. So as you can see, right in between, we have this 90%. So in this case, by the way, this is the statistics calculator. I'll put it here in case you can look it up, check it out, and if you know, keep me posted if you get it. It doesn't work. It's not my calculator. Okay, I found that online. If this is 90%, that means on each side you have 10% or 0.1 divided by 2. Degrees of freedom is n minus 1. Chi-squared of the right is 0.1 as far as the area is concerned. And divided by 2, you get 0.05 to the right. What is important to understand, the way you do the reading as far as the table is concerned, you need the area to the right. So for chi-squared of the right, the area to the right is 0.1 divided by 2 or 0.05. But what is the area for chi-squared of the left? Remember, to the left of it is 0.05. So to the right of it, for chi-squared of the left, you need all of this. That means you need 0.95. I really can't emphasize this enough for the sake of reading the table. So take a look at the table. Degrees of freedom is 24, everybody. When you look at the top numbers, on the left column, you have degrees of freedom. At the top, you have the area to the right. And so we want one of them to be 0.95. This is for chi-squared of the left. And we want one of them to be 0.05. And now you have the answers. I'm going to show you how to use a TI calculator. It is really probably not worth it that you go through the process. It's very, very long. So you go to TI calculator. In order to get to chi-squared distribution value, you have to click on Math Solver, put chi-squared CDF, and the lower, upper, and all of the above, which means you have to do this. You have to use the equation solver, lower, upper, and then it reads the answers for you. Now, I want you to come back to this PowerPoint and check all this step by step. This is not easy to do with a TI calculator, but it is doable. Okay, it uses the solver. You can even look this up online. There's a YouTube video, but again, TI is not made up for that. So what I want to show you is quickly how to use the table. I want to go back and show you the table. So let's see if we have this table. Okay, so here's the table. So remember, this was the T table, right? So when we go up, the next table is called chi-square distribution table. So you always need two things. You need degrees of freedom, which is n minus 1, and area to the right. This is the way the reading takes place. The area to the right. Okay, so in this case, you see the left column has the numbers. So those are the numbers that you have, and it's limited. So let's bring it down to number 24. So everybody can see number 24 at the bottom, the left column, number 24. Then you go to the top and you look for number 0.95. So 0.95, and you see the number 13848. And then you look up 0.05 and you read 36.415. So this is how you read the table. So when you read the table, be extremely careful. What do you need? The area to the right. All right. So in this example, we're going to come up with the chi-squared of the right and left in the case of a 95% confidence interval. And the reason it changes because when n changes, the chi-square changes. Okay, so n is 22. That means the degrees of freedom is 21. Okay, So you need the table, and so let's write the given information. When you are looking at the table, the confidence interval is smack in between. So just for the sake of argument, if you were to graph this, so what we have is 95% confidence interval. So each tail is 0.05 divided by 2. So the area to the right is very straightforward for chi-squared of the right. You have the area of 0.05 divided by 2, or 0.025. But for chi-squared of the left, you need to add 0.95, or just subtract 0.025 from 1, or 0.975. So that's the first thing I want everybody to understand. You need the area to the right. So let's look at the table. N is 22, so degrees of freedom is 21. So we are looking at degrees of freedom is 21. Now, area to the right of 0.975, and you can see the answer here. Okay, 10.28. And the area to the right of 0.025. And you can read 35.48. So those are your answers. Reading the table very carefully, class. Chi-squared of the right, chi-squared of the left, and this would be the graph. I hope it's straightforward. It is extremely important to be able to read the table very carefully. And I repeat, take a look at the given here. Let me use a different color again. This one, class, take a look at this one. This tells you need the area to the right to do the reading. This tells you need the area to the right to do the reading, everybody. Area to the right. Let's go to the next example. We want to come up with the confidence interval for estimating a population standard deviation or variance. And remember, you calculate it for variance, you take a root, becomes standard deviation. It's that simple. First, notation, we don't want to make a mistake. Sigma is the population standard deviation. Sigma squared is the population variance. S, sample standard deviation, S squared, sample variance, N, number of sample values or data, is the margin of error, chi-squared. Chi-squared of the left, chi-squared of the right. The sample is a simple random sample. The population must have normally distributed values. The requirements of a normal distribution is much stricter here in the earlier sections. And here's the formulas that showed previously. So sigma squared is between n minus 1 s squared over chi squared of the right and n minus 1 squared over chi squared of the left. Remember, chi squared of the right is larger than chi squared of the left. That's why the left side, because the denominator is larger, it becomes smaller. And again, for the sigma, you really don't have to do much calculation. When that one is done, you just take the root. So we've already discussed that, and those are the formulas. Let's find the 95% confidence interval for the variance and standard deviation of the vitamin B1 content of carton of milks. If a sample of 20 milk cartons has a standard deviation which is 1.6 milligrams. Let's first write the given. We are assuming ND or normal distribution. Okay, we are assuming normal distribution. The very first number is 95%. That's very straightforward. Confidence interval. Okay. The next number is 20. This is a sample of 20, so that's your N. Standard deviation. Now, what standard deviation is that? Notice it reads, if a sample of 20 milk cartons has a standard deviation of 1.6, that means this pertains to those 20 sample size. Therefore, this is S. So here's the given. Finding chi-squared values. We want a 95% confidence interval. That means 5% divided by 2 for each tail. So this is 0.025, this is 0.025. All right, so here's the given degrees of freedom, n minus 19. We should be able to come up with chi-squared of the right and chi-squared of the left. So for chi-squared of the right is 0.05 divided by 2. So area to the right is 0.025. For chi-squared of the left is 1 minus 0.025. So those are the values that we have, and therefore we can read them from the table. Now all we have to do, use the formula at top for sigma squared and plug in the values we just got. So we do that. N minus 1, 19, s squared, 1.6 squared, over chi-squared of the right is 32.852, and chi-squared of the left is 8.907. So that would be the right side. To do the math, you go through the process, and sigma squared is between those two numbers. Confidence interval for the variance. What about the standard deviation? Just take a rule. So what does it mean? If we want to verbalize one of them, we are 95% confident that the true standard deviation for vitamin B1 content of carton of milks is somewhere between those two numbers. By the way, milligrams. The units for the variance is milligrams squared. Milligrams squared, same thing here.
Find the 90% confidence interval for the variance and standard deviation for the price in dollars of a adult single-day theme park ticket. The data represent a selected sample of local theme parks. Assume the variable is normally distributed.
Normally distributed, so far that's good. And we can see that's 10, and we want 90% confidence. If you look at the top formula, we need to calculate and find the value of S. You have two choices. You can do it by hand, by finding S squared. The formula was summation of x minus x bar, quantity squared over n minus 1. You can go through the process and finding that. Or you can use technology such as TI calculator. I'm showing you again, I'm reminding you how to enter the data into, let's say, one of those lists like L1, L2, you name it. And then you do the calculation and it gives you everything that you need. The mean, standard deviation, 5 number, everything will be there. Chi-squared distribution table. So we want 90% confidence interval, which means we have 90% here. And the tail is 0.1 divided by 2 or 0.05. This tail is also 0.05. And so for you to figure out the answers from the table, you need two things: degrees of freedom, which is n minus 1, which is 9, and the area to the right. For chi-squared of the right, the area to the right is 0.05. But for chi-squared of the left, you want to be careful. You don't want to make a mistake. The area to the right of that is everything except 0.05. So the area to the right is 0.95. Now you have degrees of freedom, which is n minus 109, and the area to the right for each case. And now you can easily do the reading. So the main thing is, I want to make sure we can do the reading of chi-squared values. So with that being the case, all we have to do, plug in into the top blue formula. N minus 1 is 9, s squared. We happen to have it as, this is s. There are two values that they give us, s and sigma. We don't want sigma, we want s. Remember that, because it's a sample. So this is s, you're going to square that. You want to square that. So this is the number that you are interested in. 5.3124591. You square that, it becomes s squared. So now that you have the s squared from technology, you plug it in. So 9 times 28.2. Again, I would use more decimals in the beginning and do it accordingly. So divide by 16.919 for the chi-squared of the right and divided by 3.325 for chi-squared of the left. And going through the process, we end up with those two numbers. Finding the 90% confidence interval for the standard deviation, we are almost done. We just take a root because we've done the hard work already. Just take a root of both sides. And sigma is between those two numbers. So if we were to verbalize that, how would we do that? Can anybody tell us what this means? If you were to say what this means, how would you verbalize it? Anybody?
We are 90% confident that the standard deviation is between 3.8746 and 8.7402.
Thank you. Of course, the standard deviation for the price in dollars, that means between this one, the units are dollars for both cases, okay? So dollars. All right, so we are 90% confident that the true standard deviation for the price in dollars of an adult single-day theme park is somewhere between these two numbers. Here's the next one.
A group of 22 subjects took an IQ test. The subjects had a standard deviation IQ score of 14.3. Construct a 95% confidence interval estimate of the standard deviation of the population from which the sample was obtained. Assume normally distributed data.
The very first number is number 22, is the number of subjects. The next thing is this number. The subjects, those 22 subjects, had a standard deviation. So it's S or sigma, it's S because it refers to the 22 subjects. And of course, 95% confidence interval needs to be made up, assuming normal distribution. So what is given? We are dealing with normal distribution, ND for short. We have a random sample. N is 22, S is 14.3. We want 95% confidence interval, which means degrees of freedom is 21. We want chi-squared of the right and left. And so this one, and this is 95%. So the endpoints, the two tails have 5%, 2.5% each. That's the idea. So when you look at the chi-squared of the right, is 0.05 divided by 2, or 0.025. When you look at chi-squared of the left, it has 0.025 on the left. So 1 minus that on the right. That's important for everybody to see. So I want you to look at this, okay, and see again. Now we can, here, so we have a 95% smack in between. All right, so we have the chi-squared of the right and left. We use this formula at the very top in blue, n minus 1, or 22 minus 1, or 21, times s squared, which is 14.3, square it, divided by chi-squared of the right, we just came up with 35.479. And the right side of the interval is the same thing, divided by chi-squared of the left, which is 10.283. It's just a simple calculation. You plug in to the calculator, you do it with a bunch of decimals, you write the answer. If you go with one decimal, this is what we get. And this is the IQ score, and therefore we go with one decimal. But it's a good practice to keep it with a lot of decimals, and then if you want to change it accordingly. Now, you're practically done. For sigma, all you have to do is take a root of both sides. So, what does it mean? It's important to be able to verbalize it. So we are 95% confident that the true standard deviation for the population is somewhere between the two. So here's another way of writing it. Based on this result, we have 95% confidence, or we are 95% confident that the limits 11 and 11.0 and 20.4 contain the true value of sigma, or the population standard deviation. Determining sample sizes. The procedure for finding the sample size necessary to estimate S are much more complex than the procedures given earlier for means and proportions. For normally distributed populations, the table on the following slide or the following formula can be used. Everybody understands what's happening here. So we have a very complicated process. We're not going to go over that. N is 1/2 C alpha over 2 over the quantity squared, but instead a table is used. Let's see how we deal with this table. Let's quickly look at an example and answer how we deal with that. Pay attention to the table. The very first column is to be 95% confident that S is within 1%, 5%, so forth of the value of sigma. The sample size N is given. And then the next one is to be 99% confident. So right then and there, it tells you the limitation of a table. The table deals with only two confidence level. 95%, that's one confidence level. And then 99%, that's another one. Okay, so obviously there could be other confidence levels. So having said that, let's look at a simple example to see how we read this.
We want to estimate the standard deviation sigma of all IQ scores of people with exposure to lead. We want to be 99% confident that our estimate is within 5% of the true value of sigma. How large should the sample be? Assume that the population is normally distributed.
It is normally distributed, so far so good. So we want to be 99% confident. So when you look at the two tables, right then and there, you have to go to the 99%. So not the first table, the second one. The next one says within 5%. Now, look at the table, come on down and look at 5%. All you have to do, look at those two values. And what is the answer in front of it? That's the sample size you need. By the way, when it says this is at least the sample size you need, that means obviously anything larger than that will do the job. And remember the limitation of time and money. That's why we are interested in a minimum sample size. So therefore, we need to obtain a simple random sample of 1,338 IQ scores from the population of subjects exposed to lead.